Assalamualaikum. Am I audible?
Walaikum Assalam. Yes, you are.
Okay. So we are performing conversions. Yeah. So in the
Yeah.
last class, we began some conversions. I gave you some questions. Did you try them?
Oh no, I completely forgot.
You forgot?
I completely forgot to do them.
Okay. So because practicing conversions only will work, right? So no
Yeah.
matter how much you study the theory, if you don't apply them in conversions, you will not be able to, remember them, right? So
Yeah.
at least you have to spend 1 hour time in a week to perform conversions, right? So depending on your capacity, you can practice.
Yeah.
So shall we discuss these questions or shall we move to the next conversion type?
Is the next part more theory or more practical? Like as in actually doing?
Study some of the organic reagents and we have to move to advanced conversions.
Okay.
So you can try them independently and we will discuss if there is any issues in the next class, right?
Okay.
I think we can move to the next topic. Right. So this is going to be the 12th reagent, right? So we have already discussed many reagents and we have applied them in the conversions too. So our next reagent is reagent for halogens,
Okay.
right?
Okay.
So so we can categorize the reaction between halogens with organic compounds in two types. The first type is with alkenes and alkynes, right? So alkyne and alkene. I think I have already introduced these things with you, right? So if you have an alkyne or alkene, if you put Cl2 or Br2 or I2, what will happen? The chlorinate or the halogenation will occur. Halogenation, right? So this is very simple. So let's say we have C double bond, C like this, and we just put Cl2, right? So what will happen? This pi bond will break and in that place, chlorine, 2 chlorines will be added. Okay. So
Okay.
C, we have this and this and this. Let's say we put Cl2, right? Let's say we put Cl2. So here we will put Cl and here also Cl will come. And let's say we have a triple bond, C triple bond, C. Okay. Right. So let's say we put Br2. So you put Br2, both pi bonds will break and in that place we will add Br. Okay. So we have C, we have the structure. And if you put Br, we will have Br and Br, here Br, here also Br. Okay, so this type of reaction, now we haven't studied the types of organic reaction. This is called electrophilic addition, right? So electrophilic addition reaction, right? So every organic reaction may comprise 6 types. There are 6 types of organic reactions. We will study about them later. So here, electrophilic means, so we classify organic reactions based on the element that starts the reaction, right? So electrophilic means something. It will be cation, right? C plus. Here if we draw the mechanism, first this pi bond will break and this chlorine will be now the pi bond will break and the electron will be given to chlorine, right? So this is how this chlorine is added. So to the carbocation, we add Cl minus, right? So between carbon and Cl minus, there will be a bond occurring. So this is called electrophilic addition. So we have actually there are two elements, by the way. Now we have radicals, that is a separate thing. Now we have two terms, electrophilic, and nucleophilic, right? Nucleophilic. So electro means what? It refers to negative, right? Philic means what? So you might have heard about this hydrophilic and hydrophobic. Have you studied about hydrophilic? So hydrophilic means what? It attracts water molecules, right? So here electrophilic means something that attracts electrons. So it should be a positive or cation. It should be a positive ion or a cation. And nucleophilic means it attracts positive ion. So it should be a negative ion. It should be a negative ion. So this type of reaction is called electrophilic addition. That's what we have to know. Now, these are the yields, right? So these are the yields. The properties of this yield is they are colorless. They are colorless, and they will be solutions, right? Solutions. Now, if you have taken an alkyne, and if you have bubble chlorine gas, right? So if you have a bubble chlorine gas, or you can even bubble this chlorine in aqueous format also, it doesn't matter, right? So this can be aqueous, this also can be aqueous. So if you bubble it, what will happen? You will entertain a colorless solution, right? So this is all about the type 1 reaction with halogens, right? So if you move to the second type, that will be with these systems, right? So the system's name is highly repulsive systems, right? So that is not necessary. If you have these type of structures, right? So these are called now if you have this type of structures, benzene, NHCH3. Now what will happen is this hydrogen will repel electron towards the nitrogen atom. So here the intensity of negative ion will increase, right? So if the intensity of negative ion increases, the chlorine will be attracted and it will form we call tribromo substitution reaction. So this is called electrophilic addition reaction. Now I will introduce the systems that can react with this halogen, right? So this is the first system, and the second system is benzene NH2, and the third system is benzene OH. If you have these systems, and if you administer these systems with halogens, if you put halogens, Cl2 or Br2 or I2, so we can simply, in common, we can put X2, right? So in common X2. So what will happen is you will yield tribromo or trichloro substituted yield, right? So for example, let's consider this, now I will draw an example, right? So if you take this benzene OH, and you put Cl2 gas, right? So the yield will be like this, right? So the yield will be, here OH is there, but here if you put Cl2, now in the ortho and para, in the ortho, opera, and meta positions, have you heard about this ortho, para, meta?
No.
No, okay. So you haven't started organic chemistry yet?
We did, but the only thing we've done right now is the what's it called? The way you name them.
Did you get any notes from your, do you have any resources so that I can explain them?
For the names? That's all we've got so far. Only the names.
So you have just studied the nomenclature.
Yeah, just now.
That's all. Other than that, you didn't study anything.
No, we just started it on Friday.
Okay. Right. It doesn't matter. We can study advanced things so that now if you know more, then it will be easy for you in the examination as well, right? So yeah. But these are very basic things, right? So there is
Okay.
nothing here. So if you put Cl2 here, here, and here, right? So next to the OH, we will have 2, right? So it will be symmetric and skipping this position or skipping this node in the meta position, right? So this is called ortho, and this is called meta. So in this position, Cl2 with chlorine will be added. Chlorine. So this is a white color precipitate. Right? So what you should understand here is, if you have to administer organic compounds with halogens, there might be 2 types of reactions. The first type is with alkenes and alkynes, right? So if you put alkenes and alkynes, so these are the outcomes or products, right? So what will happen? The pi bond will break and there the chlorines will be, or the halogens will be added. So this type of reaction is called electrophilic addition reaction. And the properties of the solution, or the properties of the eel, are colorless and solution. But the second type is, if you have these 3 systems, if you put NH2 or OH, only with these 3 systems, if you put halogens, you will encounter a white color precipitate. So can you just try to draw the structure for these things? You put NH, CH3, we put Br2, and here NH2, we put Cl2. So can you just try to draw the eels?
Okay, so then we'll have the same ring, or the benzene ring. And then you will still have the NHCH3. And you'll also have bromine. We'll put them here and here to minimize. Is that correct for the first one?
Okay. So here what will happen is, now this is the system that you are considering, right? So next to it, we have 2 nodes. So in this node and in this node, we will add Br. And skipping this node and this node, we have to add here another Br. So this is wrong. So this is how it should appear, right? So here simply Br, here also Br. So next to the functional group, there are 5 nodes, right? So in the adjacent nodes, either side, we have to put Br, and skipping the next nodes from both sides. Now the next thing is only 1 node is remaining. Here we have to put Br, that's all. And here again the same thing, right? So here we have benzene, and here NH2 is functional group. So if you put
either side of it,
here
Cl,
and here,
Cl.
and then here, right?
Okay.
Cl. So all these will be white color precipitate. Generally, if you put these systems, only Br2 and Cl2 will react. I2 will not generally react. We don't put I2. Okay. So that is just a common practice. Okay. So that's all about the 12th reagent. And now we'll move to the next type, that will be HNO2, right? So nitric 3 acid, right? So HNO2, the name is what? nitric 3 acid. Why? Because it might have nitrogen may have +3 and +5 oxidation state. So here it is HNO2. In HNO2,
Okay.
the oxidation number is +3, right? So do you know how to determine the oxidation number?
Yeah.
Right?
You equate it to 0 and then you find the known one, which would be hydrogen, and you solve it like that.
Yes. And we can even call this as nitrous acid also, nitrous acid, right? So these are the names, right? So that doesn't matter. Okay. So if you have NH2, right? If you have NH2, if you put HNO2, it will convert NH2 as OH2. That is the function of this nitrous acid. For example, it can react with both aliphatic and aromatic compounds, right? Aliphatic means what? Without the involvement of benzene. Aromatic means benzene ring is present. We already discussed aliphatic. We can classify organic compounds in aliphatic and aromatic, right? So aromatic means we have benzene ring, but in aliphatic compounds, we don't have benzene ring. For example, if you have benzene NH2, right? So in a conversion, you want to form OH. So simply you have to put HNO2, right? Simply HNO2. And let's say we have RCH2NH2, right? So now in the answer, now you have to convert it to CH2OH. Now what you have to do is if you encounter this one, and in the question we have this, right? So you have to think what you can put. So you can simply put HNO2. Okay.
Okay.
Then in addition to this HNO2, you might want to put NaNO2 and HCl, but that is not mandatory, right? So you can, if you wish, you can put NaNO2 and concentrated HCl also, but that is not necessary. If you are given these substances, you can put if the reaction doesn't occur. Otherwise, not necessary. Okay. Right. So now we have a point in order to produce this diazonium chloride, right? So this is used in dye production, right? So you might want to produce dyes, right? Colorings. So this is how organically the dyes are produced in the industrial settings. Now, from the aniline, right? From aniline, if you reduce the temperature to 0 to 5 degrees Celsius, you might produce a diazonium chloride salt, right? So I will write the reaction here. So now everything can be now I can give you the sentence format also, but if I draw this reaction, you might be able to interpret it, right? So let's say we have aniline NH2. Now you put this NaNO2, but compulsorily you have to put del HCl, and you have to keep the temperature 0 to 5 degrees Celsius, right? So very minimal temperature. So you will produce this diazonium chloride. Diazonium chloride means benzene N2 plus Cl. N2 plus Cl minus. N2 plus Cl minus. Now this is called diazonium chloride. Diazonium chloride. Right? So this is basically a dye. Right? So now why we need to keep this temperature is, now if you want to produce this diazonium chloride, you can put NaNO2 and diluted HCl. So if you want to produce diazonium chloride, diluted HCl is very important. Otherwise, it will convert to OH, right? So if you merely put NaNO2, the entire system will become OH, right? So instead of this, we will have OH. But if you want to produce diazonium chloride in order to produce dyes, we have to compulsorily use diluted HCl. But this diazonium chloride is stable only in the low temperature. So you have to keep the temperature 0 to 5 degrees Celsius. Then only it will be present. Otherwise, again, it will convert to OH. Right? So the point is, if the temperature is increased above 10 degrees Celsius, instantly it will convert to a phenol. It will convert to phenol, right? So should I tell this in sentence format? So I can simply type over here, right? Otherwise, yeah. Right. So you have understood, right? So what I told is, if you have aniline, if you want to produce diazonium chloride, in order to produce dyes, we have to keep the temperature 0 to 5 degrees Celsius with diluted HCl. But if you merely put NaNO2, it will become like this, right? It will become like this. But this is different. This one is different from this one, right? Phenol. So this is called diazonium chloride. Now, if you increase the temperature, so after producing this diazonium chloride, if you increase the temperature, let's say you increase the temperature to 10 degrees Celsius, you keep the temperature above 10 degrees Celsius, again, it will become OH. It will become phenol. Okay.
Okay.
Now, this is possible only in aromatic compounds. But if you put aliphatic compounds and the same conditions, it will not produce. It will not be produced, which means even though if it is produced, it is not stable because only aromatic diazonium chloride are stable in the low temperature, but aliphatic diazonium chloride are not stable. It will instantly convert to alcohol, right? So the point is, aliphatic diazonium chloride is not stable, so, right? So for example, let's say we put RCH2 NH2, right? So if I put NaNO2 plus diluted HCl, right? And let's say we keep the temperature from 0 degree to 5 degrees Celsius. So we can say it. So according to what we have already studied, it may produce RCH2, and instead of this, what will happen? N2 plus Cl minus, right? N2 plus Cl minus. But this aliphatic diazonium chloride is not stable. This is not stable. This is not stable. It will quickly convert to alcohol, right? So it will become RCH2 NOH, right? Instantly. So have you understood this? So I have taken this substance and I put NaNO2 diluted HCl, and let's say we make the reaction happen in refrigerator, right? So what will happen? Will you get this diazonium chloride or phenol? Sorry, alcohol. It might be an intermediate product, right? So the aliphatic diazonium chloride might be an intermediate product, but this is not stable. Even though it is formed, it will instantly convert to alcohol, right? So, so what I'm going to do, what I'm trying to say is, if you want to produce dyes, you have to start with an aromatic compound, aniline. Okay. Right? So from aniline only, we can produce dyes, right? So we'll see how dyes are produced in industrial chemistry. I don't know if they have included the production of dyes. Let's see, okay? Right. Now we will move to the last reagent, that is Grignard reagent, right? So is there any confusions here? Have you understood everything regarding HNO2? So if you have NH2 group, if you want to convert it to OH, simply you have to add HNO2. It can be applied to both aromatic and aliphatic organic compounds, but the theory regarding this aromatic compound is completely different when we include diluted HCl and low temperature. So in this scenario, you can produce diazonium chloride, right? So this will be used for the production of dyes. But if you increase the temperature more than 10 degrees Celsius, it cannot be stable. It will convert to phenol. But As far as aliphatic disonium chloride is concerned, that is not stable even in the low temperature. So if you perform the task or if you perform the experiment, it will quickly convert to alcohol, right? So that's the summary of this HNO2. Okay.
Okay.
Now, Grignard reagent, right? So this is very famous reagent in the entire organic chemistry, right?
Mm.
Grignard reagent. Okay. So first of all, we have to know the general format of a Grignard reagent, right? So general form is we have RMGX. RMGX. So this is the general format, right? So if we have, let's say, CH3MGX, let's say benzene CH2MGX, right? So these are called Grignard reagents. Okay. So in the R, we might have any hydrocarbon. Okay. First of all, we have to know about the types of Grignard reagents and their production, right? First of all, we have to produce Grignard reagent before we administer to any other organic compounds, right? So here we have aliphatic Grignard reagent and aromatic Grignard reagent, right? So now we'll see preparation of Grignard reagent. Number one, aliphatic, right? So we'll see aliphatic. So aliphatic can be started. Aliphatic Grignard reagent can be formed from methane gas, right? So if it is aliphatic, so we have to start with methane gas, CH4, and we have to put Cl2 and sunlight, right? So this reaction should happen under the presence of sunlight. So it will produce CH3Cl first. And then again, if you put magnesium and dry ether, it will produce CH3MgCl. Okay, is that clear?
Mm.
Right?
Okay.
So if you put magnesium and dry ether, this magnesium will come and it will be inserted in between CH3 and chlorine. So it will produce CH3MgCl. So this is our aliphatic Grignard reagent. So we start with methane gas, we put Cl2 under the presence of sunlight. So it will produce CH3Cl. So this is what this is called radical addition reaction, right? So we'll study radical addition radical addition reaction, right? So radicals means, have you heard the term radicals?
No.
How do you call this symbol? Square root symbol.
Yeah, square root.
This is radical. And if you have a lone electron on an element, that is called radical in chemistry, right? So here, okay, we will study about these things later, right? So this is how aliphatic Grignard reagent is formed or prepared, right? So can you describe how aliphatic Grignard reagent is formed?
So you get so you react something in the you react a alkane in the presence of sunlight with chlorine, and then from there you react it with magnesium and dry ester.
Yes. So you put magnesium and dry ether, right? Not ester.
Oh, ether.
You will have CH3MgCl.
Okay.
And then this is very important, aromatic.
Okay.
Next, aromatic Grignard reagent, right? So the second one is aromatic. Aromatic means we have to start with benzene. Here, if you want to start with benzene, benzene can undergo only 4 reactions, right? So we'll study the 4 types of reactions that benzene can undergo, right? So here, if you put Cl2 and CH3Cl, CH3Cl. Only we cannot add, this is substitution, right? So this is electrophilic substitution reaction. Here we will put benzene Cl. Again, if you put magnesium triether, when you study the reactions with respect to benzene, you can easily understand. Now you just remember only 4 types of reaction can be done on a benzene ring. Only 4 types of reaction. Among them, this is a type of reaction. So this is called halogenation on benzene ring. So if you want to add halogen on benzene ring, so we've already studied, right? So if you have benzene OH, if you put Cl2, you can substitute Cl here, right? But if you want to perform, or if you want to substitute chlorine on a pure benzene ring, you have to use CH3Cl also. You cannot use chlorine alone. This, if you put chlorine alone, this reaction won't happen at all, right?
Okay.
So that is okay. Now Cl2, CH3Cl, you put Cl here, right? So definitely Cl should be added, right? So this is called halogenation on benzene ring. Adding halogen on benzene ring. Again, if you put Mg and triether, so what would you get? Benzene is there, and then MgCl, right? So magnesium will be added in between benzene ring and chlorine, right? So this is how aliphatic and aromatic Grignard reagents are formed. Okay.
Okay.
Right. So we have around 10 reactions with respect to this Grignard reagent. We will see them one by one. So have you clearly understood how Grignard reagent is prepared first?
Yes.
Okay. So we will discuss the reactions with respect to benzene ring one by one. So the first one is type 1, right? So type 1, the first one is acid aqueous solution with acidic aqueous solution. I'm very bad at spellings, right? So aqueous. So aqueous, right? So while I'm writing, I may commit some spelling mistakes, so you don't worry about that, right? So aqueous.
Yeah, okay.
So this is aqueous solution. So here the thing is, if you put first of all, you have to dissolve these acids into water, right? So it might be a strong acid or weak acid. So if you add water to any acid, you may produce hydronium ions, H3O plus, right? So let's say we take some water, H2O, and we dissolve HCl, or we add H2SO4, or we can even add CH3COOH, right? Acetic acid. So the yield, what would it yield? It will yield H3O plus aqueous. H3O plus aqueous. Now we have to form this H3O plus aqueous, and let's say we have RCH3 or RMgX, right? So let's take this RMgX. So this is what? This is our Grignard reagent. Now, if you put this H3O plus or the acidic aqueous solution, here what will happen is hydrogen will be replaced in the place of MgX. So we can produce RH. So can you understand what has happened here? If you put H3O plus, instead of this MgX, we will put H. That's all. Okay. Right? Is that clear? So if you, under the presence of acidic aqueous solution, Grignard reagent, in the Grignard reagent, MgX will be removed and in their place, H plus will be substituted. Okay. Is that clear? Are you there?
Oh, sorry, yeah.
Okay. So this is the first type, right? So you put acidic aqueous solution to Grignard reagent so that you can produce an alkane. For example, let's say we have CH3MgX, right? So from Grignard reagent, you have to make methane. So you just put H3O plus so that you get CH3H. So this is literally equal to CH4. Yeah. Okay. And let's try some other questions. And let's say we have CH3, CH2, MgBr, and you put D3O plus, right? So we've already discussed, right? So the isotopes of hydrogens, deuterium and tritium and hydrogen, right? So simply, if you put D3O plus, instead of MgX, we will put D. That's all. Because why? If it is hydronium, if it is hydrogen, we have to substitute H, and if it is deuterium, we have to just substitute D, right? So instead of
Okay.
this MgBr, we will put D. If you put D3O plus, right? So D3O plus means the water, but we have used deuterium in order to form water, right? So generally H, right? So H means 1, 1, right? So we already discussed, right? So these things, the isotopes of hydrogen, isotopes of hydrogen we discussed, H11, deuterium and tritium, right? Tritium. So it is 1, 2 and this is 1, 3, right? So they contain different mass numbers. So these are called isotopes. So if you put D3O plus, so the output would be, or the yield would be CH3, CH2. Here, instead of this MgBr, you just put D. Why? Because if it is H3O plus, hydrogen is produced, hydrogen is replaced, right? But if you put D3O plus, deuterium will be replaced. Is that okay?
Yeah.
Okay. And let's say we have benzene CH2MgCl. CH2MgCl. You put H3O plus. So here the yield would be CH2, another H, so that would be CH3. Yeah?
Yeah, okay.
So that's all. So this is very simple. And now we'll move to the next type, that is with dry carbon dioxide, right? So the second type is with dry carbon dioxide. So type 2, Grignard reagent with dry CO2. Okay. Now, first of all, we have to understand the structure of carbon dioxide. So CO2 means carbon is there, double bond O, double bond O. Okay. Now we have RMgX2. RMgX2. Now here, since oxygen is more electronegative than carbon, here delta minus will be formed. Here delta plus will be formed. Here delta plus will be formed. So what you would do is here Mg plus, here we will have plus and here we will have minus, right? Because magnesium is a metal. So magnesium will comprise positive charge. That would be delta positive. And here delta negative, because the carbon will tend to attract the electrons towards itself. So magnesium will encounter a positive charge environment, and the hydrocarbon group, R group, will have negative charge group. Okay. So how we are going to predict the yield is, now let's say we take this structure RMgX, we put CO2. So how you have to write it is, now you see C, right? C double bond O, right? Because what will happen is this delta minus, this delta plus will attract this delta minus, and this delta, this MgX will attract this. Now this MgX containing positive ion will attract this delta minus. So we are going to combine them, right? So RC double bond O, and here also double bond O. But we are going to eliminate this pi bond, and this MgX in the Grignard reagent will come and join with this delta minus, right? So MgX, okay, MgX. And then here with this carbon, this R will join, right? So R will come and join here. Is that clear?
Okay.
right? So how we have to write this is now carbon. Now this is the structure of carbon dioxide, right? So since oxygen is electronegative, it will experience delta minus charge. And here, since magnesium is metal, it will experience delta plus charge. So oxygen will attract this MgX group. And here, this will come and join with this oxygen, right? Because definitely, if it wants to encounter this delta minus, the delocalization of pi bond should occur, right? So it should have the pi bond is no longer available on the between carbon and oxygen. So oxygen will attract this MgX. And then again, due to the positive charge on carbon atom, this R group will come and join. Okay, this R group will come and join. Now, again, if you put H3O plus, again, if you put H3O plus or water, what will happen? This MgX will come as H, right? So, again, if you put H3O plus, the output will be carbon is there, double bond O, R is there, O is there, H, OH. So we have actually created a OH here, right? So this is the outcome. So we have literally created oic acid, right? Carboxylic acid. This is actually carboxylic acid. Is that okay? So we have studied, if you have Grignard reagent, the charge distribution will be like this, right? R will comprise or will get negative, delta negative charge. Delta negative means slight negative charge. And MgX will comprise delta positive charge. So since carbon dioxide comprises two different atoms, oxygen is more electronegative, so it will have delta negative charge so that it will attract this MgX group and combine like this. And again, this R will come and join with this delta plus. And then again, if you put H3O plus, you can produce carboxylic acid. Okay. Now I will give you some techniques. Right? You can try it. Okay. So let's say we have CH3 MgBr and we put CO2. Okay. And again, we have CH3 CH2 MgBr. We put CO2. And again, let's say we have benzene CH2 MgBr and we put dry CO2. These are all dry CO2. Huh? Dry CO2. Okay. Can you try to draw the outputs on the screen, or you can draw the yields on a piece of paper and send me as well.
So
Okay, fine. Okay, that's fine. So in the first step, if you put only dry CO2, you cannot
Mm.
produce this H, right? So again, if you want to remove this MgBr, again you have to separately put this H3O plus or water.
Yeah.
Okay. It should be done in separate steps.
Okay. And then I get the H3O plus. Which reacts to create. So you keep the double bond here. And then you'll go. Mm, okay. And then
Okay, fine. Okay, that's okay. Yeah. And what about
and
the
then
third?
now, yeah, just give me 1 second to think. So, mm, okay. Oh, is this just gonna be the same? Think about it. You'll have your. Hmm. Is this just gonna follow the same thing?
Yeah, the same thing. Only
Okay.
difference is instead of CH3, CH2, we have benzene.
Yeah. And then here. Is that correct?
Yes, COC. Now you have to add this CH2. It's not correct.
Hmm. Oh wait, hold on. Actually, give me 1 second. Wait, I think I switched to this. There's this.
Very good, very good. Yes.
Like CH2 there and then MgBr.
Yeah.
Okay, because that's part of the carbon chain. Yeah,
Yeah.
okay.
Yeah.
And then I'm gonna run as. Let me just properly write it. And then here, let's see. That
Yeah,
thing
that's fine. So
disappeared.
again, the same structure, but instead of MGBR, you would put HBR.
Yeah.
Okay. Right. So that's all. Now we can move to the third type, right?
Hmm.
Okay. So can you erase
Yep. Give
these
me
anatomy
1 second.
points?
Yep. Yeah.
Right. So the third type would be with carbonyl system or carbonyl group, right? So the third type is with carbonyl group. So the same thing, but instead of one oxygen, we will have CH3 or R group, right? So first of all, we have to understand the structure of this carbonyl. So we will have C double bond O, C or H. Here carbon or hydrogen, here carbon or hydrogen. So we are only concerned about the charges on one CO bond, right? So okay, here delta minus, here delta plus. We have R MgX. So here plus, here, sorry, see here plus, here minus. So what will happen is this minus will come and join with this plus, and then this MgX will come and join with this oxygen, right?
Hmm.
So if you look at some examples or the general thing, so if you put RMGX, so can you try to predict the yield? So we have C, O, right? And here C, here CH, right? So this is the structure of this carbonyl, and I'm going to use this blue color for indicating what are coming and adding to the carbonyl group, right? So here this R will come and join, and MgX will come and join here, right? And then again, if you put H3O plus, this MgX will be removed and hydrogen will be added. That's all, right? So I will give you some examples. So let's say we have C double bond O, CH3 and CH3. We put, let's say RMGX. RMGX. Not RMGX, I can take a particular example. Let's say CH3MGX or CH3CH2MGX. CH3CH2MGX. Okay, so you are supposed to write the thing. And let's say we have CH3, C double bond O H. To this we put CH3 MgCl. That is CH3 MgCl. And then again, we put, let's take this ketone. We put hydrogen, C double bond O, hydrogen. So we put CH3 MgCl again. Yeah, go ahead.
Okay.
Yeah, can you try to write down the yields for these reactions?
Okay. So hmm, oh, oops. Let me write it a little bit lower.
Done?
Yeah.
Oh, why were you silent? Okay,
I was just double checking, making sure.
okay. Uh, right, so simply you add this to this carbon, so that is fine. And here CH3, CH3, all VX. And here CH3 should be added. And this is okay, this is fine, everything is fine. And then again, again you have to put H3O plus, and yeah, that's okay. Yeah, that's fine. Now we can move to the next type, that is with alkyl groups, right? So that is next type, the fourth type with alkyl groups. Type 4, alkyl group. Okay. Okay. So alkyl group. So alkyl group in the sense we will have Rx, right? And here
Yeah.
might be CH3Cl or CH2, CH3, anything, right? So simply what we will have is instead of this Cl, for example, if I explain this using examples, can you erase these things?
Okay. Sorry. Done.
Okay. So if you have Rx and you put this R dash MgCl, right? So let's say R dash X and we put R MgCl. Okay. So what will happen is this R and this R dash will combine to form R dash R and then plus this Cl or whatever it is, right? So if you put, we can use MgX, general form, right? MgX, right? So this X and this MgX will combine together to form MgX2. That's all. Okay. For example, let's try these examples. We have, let's say, CH3Cl and we put benzene MgCl. Benzene MgCl. Okay. So you have to predict.
Okay.
And then let's say we have CH3CH2, CH3CH2, Br. Okay. CH2CH2 Br. And we put CH3MgBr. CH3MgBr. Now, if you want to add the number of carbons in a conversion, we already discussed we can use the sodium derivatives. Yeah, sodium derivatives in the last conversions. Do you remember? If you want to increase the number of carbons during a conversion,
Yeah.
the
You
first
use the
method is
sodium
to use
derivatives.
sodium derivative. And the second
Yeah.
method is to use Grignard reagent, right? So now let's say here we have only one carbon, but in the yield we will have more number of carbons. Yeah, here the number of carbons is literally increasing here. Okay, so you have to predict what will happen. Okay, so can you do this?
Okay, so you react that with that. So you'll get okay.
Okay, fine. So now we'll move to the type 5. Yeah, that's okay. Right. So type 5 is with acid halide or ester groups, right? So with type 5 acid halides and ester groups. Okay. Right. So now we have to know the general structure of acid halide and ester group, right? So acid halides would appear something like this, right? So we might have anything here, C double bond O NX. And ester means R C double bond O and here anything, right? So it may be anything, R dash we can say. Now, we have to be more obsessed with these acid halides because that is mostly encountering reactions, right, in the examination also, but we don't want to bother about this ester involving reactions. So let's say we have R, C double bond O and X, and we put R dash MgX, right? So here what would happen? So simply this R dash will come and join with this carbon and this MgX will join with this oxygen, right? So that is obvious.
Yeah.
We have already discussed how this happens, right? So R
Yeah.
and C, O, this is C, right? C, O, MgX, and here we have R dash and here also, oh, R dash. So here what will happen is, this R, okay, so I'm sorry. R will come and join here, R dash. Okay, so let me explain from the beginning. Okay, so already we discussed if you have this alkyl group, the X will come and join with this MX2, right? So if you have R,
Yeah.
let's write everything clearly. Let's say we have R C double bond O X and we put R dash Mg X. Okay. Now
Okay.
this X, if you have X, this X will come and join with this MgX to produce MgX2, right? But
Yeah.
around the carbon, we should have 4 bonds, right? We should have 4 bonds. Okay, and another
Okay.
MgX will come and join with this oxygen. Okay, so here this is how the product will appear. So if you use different colors, you can understand. So using R dash MgX, right? So here, if I keep this acid halide as a reference, I will have R, C, and this pi bond should go, right? So O will be alone. So with this O, MgX should come and join. So what will happen is this X will release and go with another MgX to produce MgX2. So here two bonds are needed. Two bonds are needed. And we will add this Grignard reagent in excess amount. So if one MgX comes and join with this oxygen, another MgX can come and join with this X, right? So to produce MgX2. So we will have R dash. Two R dash will come and join. So from the Grignard reagent, the alkyl group will be will be added to the acid halide in 2 directions, in 2 positions. With the carbon in the acid halides, from the Grignard reagent, R group will come and join twice, right? But in the earlier case, only one R will come and join. Yeah. Okay.
Okay.
Is that clear? Okay. And again, the same thing, right? So instead of this X, we will have OR, right? So I will draw the general structure for that one also. So let's say we have R, C double bond O, anything. Here it can be anything, right? So if you put R dash MgX, what will happen? Here we have R, C, and here O, and to this O, MgX will come and join. So this group will leave. This group will leave because this is a negative group, right? So negative charge carrying group. So this will leave, and here R dash from the Grignard reagent will come and join twice. Okay. Is that clear?
Yeah. Okay.
So now we will do some questions. Right. Let's do one by one. So let's say we have CH3, C double bond O, Cl. Let's say we put CH3 MgCl. So how would the yield appear?
So if you put
So simply you
CH3,
have to remember this CH3 from the Grignard reagent. If you have used acid halide or ester, the R group from the Grignard reagent will come and join with the carbon in the acid halide or ester twice, right? So simply you have to think, this is how you have to get the idea. This CH3 will come and join with this carbon twice. So you can start like this, CH3, C, O, MgX, right? And here this CH3 and this CH3. These two CH3 are from this Grignard reagent.
yeah, okay.
Now you can write the second one, right? So the second one, benzene, C double bond O, Cl. And we put, let's say, benzene, MgCl, or yeah, benzene MgCl. Okay, can you try to sketch the diagram of the yield?
Okay, let me think first. Okay, right, so it'll just be this.
Actually, as I explained you already, here for this reaction, we will require 2 moles of CH3MgCl. Why? Because for combining with this oxygen and for combining with this Cl. So we need 2 moles of CH3MgCl to combine with 1 mole of acid halide. That is very important.
Okay.
Okay. Yeah.
Okay.
You can write this in 2 steps also. 2 steps in the sense, first you remove this chlorine and then again you like that also, but you understand, right? So we will require 2 moles because we will have to add MgCl to this chlorine present in the acid halide, and then with oxygen also we need to combine 1 MgCl. So we require 2 moles of Grignard reagent to combine with 1 mole of acid halide. Okay, if you want, you can write plus MgCl2. So that is a byproduct, right? That is a byproduct. Is that clear to you?
Yeah.
Okay.
So for this one,
Otherwise, if you need, you can write this way also. Before that, I will explain that, right? So if you want to write the steps separately, first what will happen? This Cl will remove and MgX will come and join there, right? So if you want to write in 2 steps, right? So let's say we have CH3, but this is not necessary, right? C double bond O, Cl, right? So first we put 1 mole of CH3 MgCl. What will happen? This Cl will come and join with this MgCl2 to produce CH3 C double bond O CH3, right? CH3. Yeah, is that clear? Is
yeah.
that clear? Again, if you
Okay,
put
yeah.
another CH3 MgCl, what will happen? This is what we already studied. This CH3 will come and join here, right? So this CH3 will come and join here. So this product will be formed. Yeah. But without writing in separate steps, I have just written in one single step, but I have mentioned that I need 2 moles of CH3 MgCl2. That's all. Okay. Is that clear? Is that clear?
Yeah.
Okay.
Yeah.
Right. So we can try the second one. So benzene, C double bond O Cl, and we put benzene MgCl. Okay. Benzene MgCl. Yeah, go ahead.
So then you put, see, done, I think. And then
Uh,
plus MgCO2.
yeah, what you have to do is, if you have this Cl, now here we will add benzene. Yeah, that's correct. Okay, that's now. And the third one, okay?
Okay.
The third one, you can try this. Get another page there. So let's say we have benzene, CH2, C double bond O, Br. Okay. So we add
Okay.
CH3 MgBr, CH3 MgBr. So what's the product? Simple. Simple. You can simply say this CH3 will come and join here and here also. Right? CH3, CH3. Yeah. Is that clear?
Okay.
Okay. And can you try this? Benzene, CH2, C double bond O, OCH. This is for ester. And oh, I didn't mention what I have read, right? So benzene, MgBr. Benzene MgBr. Okay.
Okay. So if we do this, ooh, okay. Okay. Hmm. Okay. And then now here's what I want to show that. Uh, Mm,
Done?
uh, I'm not sure. I'm just thinking because
Okay.
there's an extra
So, yeah,
CH3.
what is happening here, right? So this is the
Yeah,
structure of ester, right? So I told you
yeah,
the breaking of bond will happen at this point. Here, at this point, that nothing, right? So instead of X, we have this. So
mm,
this benzene will come and join here and here. That's all, right? Yeah, that's
okay.
discussed already. Here,
What about yeah,
whatever we have, we will just break it. Where is that? Here, right? So at this point, this will break and R dash will come here and here. That's all, right? Okay.
yeah,
Right. So we have benzene, CH2, C double bond O, and then benzene from Grignard reagent, and this benzene is also from Grignard reagent. Okay, that's all. Yeah.
yeah.
Okay. So yeah, I will give you two more questions. Okay. Right, try these two. Let's say we have CH3, CH2, C double bond or Cl. We put CH3 MgCl, and we have CH3, CH2, CH2, C double bond or Br. We put let's say benzene MgCl. Mm. Yeah, try these two. Very simple.
Okay, so you would break it there, and then you would just go that, and then CH2, and then you put the couple CH3s. And then you would put a MgCO2 over here. And then, yeah, let's go, just start off down here. You would go,
Okay, that's fine. Right, you understand. Now
Yeah.
we will, okay, so far we have discussed the 5 important reactions between organic reagents, organic compounds, and Grignard reagent, right? So we have 5 more. They are not very important, but anyways, knowing them might be beneficial. So we can say extra reaction between organic compounds and Grignard reagent, right? So the first one is, let's say we have this type of structure, RMgX, right? So here we'll take RMgX, a Grignard reagent, and let's say we put R dash C triple bond CH, right? Now what will happen is, again, so this is an acidic one, right? So this will comprise positive charge and this will comprise negative charge, right? Negative charge. So what will happen is we will have R and R dash. This R dash and this R will come and join, right? Sorry. No, sorry, because this is acidic hydrogen. This one is acidic hydrogen, okay? So if you have R dash C triple bond CH, we have already studied, right? So if you have a hydrogen attached to a triple bond carbon, that will be acidic hydrogen. So what will happen is this R dash, this H, this hydrogen will anyways release, right? Because that is acidic. So if it release,
Yeah.
it will be negative, right? This will be negative. This will be negative. So we have MgX plus here. So we will have R minus NH plus, right? So if it is negative delta minus, if it is negative, this H plus will come and join with this R. So we have RH plus
Okay.
R dash C triple bond C MgX. Is that clear?
Okay. So R bonds to the hydrogen and R dash. Okay. Okay.
Okay, right. Because since this hydrogen is acidic hydrogen, that will be released as H plus. So that H plus will come and join with the alkyl group in the Grignard reagent. And MgX will come and join with the rest of the part in the given compound. Okay, that's it.
Okay.
Right. So this might be important, but the remaining things are not very much important, but you can just know them, right? So let's say we have R MgX. If you put H2O, right? So it is like acidic aqueous solution. Simply RH will come. RH will come. And let's say we have the third one is RMgX is there. And we have ROH, R dash OH, any alcohol. If you put any alcohol, again, it will yield RH. And if you put ammonia also, we can produce RH, right? So now after performing this Grignard reagent, in order to produce alcohol, okay, alcohol, or in order to replace it with hydrogen, we can use either acidic aqueous solution or water or alcohol or ammonia or even RNH, right? So these are the things. R, MgX, this is not very much important, right? So NH3, we will get RH. Again, if you take the fifth one, R, MgX, if you put R dash NH2, again we will get RH. Okay. This is just for your knowledge, but you have to understand how the first reaction happens only. But the remaining things are, if you have a Grignard reagent, in order to replace MgX with hydrogen, you can either use, you can use the following substances, either water, alcohol, ammonia, or RNH. That's it. Now we will move to the advanced conversions, right? So we are going to perform some more conversions. So this is called alpha hydrogen, right? So if you hear, this is called alpha hydrogen. Alpha hydrogens are very acidic. Anyways, you don't want to worry about that much. We will now move to conversions. Yeah, so after performing some conversions, we can move to the benzene and then we can study the mechanisms. Okay. Right. So we will start from the basic things. We have already done some conversions. But after that, we have studied HNO2, halogens, and Grignard reagent. So in the advanced conversions, we will be involving Grignard reagent also. So we are going to actually increasing the number of carbon atoms in the substrate and the yield. Yeah. Right. So let's say we have CH4 from methane. How are you going to produce this? Right. So the first one, we have CH4, and from this we are going to produce CH3D. Okay. How can you do this? So if you see CH4, we have studied the preparation of Grignard reagent, right?
Yeah.
Okay. So we simply put Cl2 and sunlight.
Mm.
Yeah? Sunlight. So we will get CH3Cl, right? CH3Cl. Okay.
Okay.
Now what we have to do is we have to form D. So if you have to add D, if you have D3O plus and we have CH3 MgCl, if you put D3O plus, you can replace D. Again, we can simply put magnesium ether, right?
Yeah.
This is how we are going to perform conversions. So getting idea is very important. So for that, you have to be thorough in the theory.
Mm.
Okay, right. Now the next one. So the second one is, let's say we have benzene, and from the benzene, we have to add D, deuterium. How can you do this?
This, so you want, okay. You would
See a mere benzene. I haven't taught you the 4 reactions happening on benzene ring, but I already told you if you want to add chlorine, you have to use Cl2 plus
sunlight.
CH3Cl, right?
Oh wait, yeah, for benzene, yeah, CH3Cl. Because it's aromatic, right? Yeah.
Yeah.
So
Sorry. Not CH3Cl, FeBr3, right? So we understand. I already explained. So we will study the, now before that, if I teach you the, yeah, so we will first discuss the reactions happening on benzene, right? So reactions on benzene. These can be electrophilic substitution reaction. So there are 4 types: nitrogenation, halogenation, alkylation, and acid halide. We have to add acid halide, right? So
yeah.
Friedel reaction. That is called Friedel reaction. Okay.
Okay.
So I will just introduce these things, right? So nitrogenation means if you have benzene, if you put HNO3, concentrated HNO3 and concentrated H2SO4, HNO3 plus concentrated H2SO4, H2SO4. Here, this is the reactant, and here this is the catalyst, right? Because the reaction rate of this reaction should be very less, so we have to increase it. So that's why we use this catalyst in order to make the reaction happen, because the activation energy involving in the benzene reaction is very high. That's why we have to use this what do you call, catalyst, concentrated H2SO4, right? So simply the electrophile, right? Here the thing that starts the reaction is electrophile. So the electrophile is NO2 plus. NO2 plus will come and join NO2. Okay. If you put benzene, concentrated HNO3 and concentrated H2SO4, the electrophile NO2 plus will come and join on any node of the benzene, right? And let's say we have benzene and we have to add halogen, right? So we have
Yeah.
to use X2 or FeX3. FeX3, which means if you want to put Cl2, FeCl3, if you want to add Br2, FeBr3. So what will happen? The chlorine will come and join. But if you have double bond or triple bond, or otherwise, if you want to add, no, but if you have this kind of things, right? If you have benzene OH, if you have benzene OH, the repulsion is very high. The electronic repulsion is very high. So it comprises a lot of negative charge because high OH will repel a lot of around 270 delta negative towards the benzene ring. So the benzene ring is highly negative. So once an electrophile is arrived, it will quickly come and join with the benzene. So that's why if you put Cl2 alone, it will produce OH, here Br, or Cl, here Cl, here Cl, right? Because the electronic repulsion is very high here. That's why we have to test. But benzene is not like that because there is nothing to repel electron around the benzene ring, right? So the negativity of the benzene is very less here. So this cannot happen without a catalyst. So the FeX3 is a catalyst here because it will induce the electronic environment or the negative environment in the benzene ring. So that is based on mechanism. But what you have to do, what you have to know is, if you have a mere benzene, if you want to add halogen, you have to use X2 plus FeX3, Cl2 FeCl3 or Br2 FeBr3. Okay.
Okay.
Right. And if you want to add an alkyne, right? So if you have, let's say, we have benzene, right? So if you want to add CH3Cl, you have to add anhydrous aluminium chloride, anhydrous aluminium chloride, AlCl3. We will study these things in detail later, but I wanted to just introduce this, right? So you just know that if you want to add chlorine to a benzene ring, you have to add Cl2 plus FeCl2. Yeah?
Okay.
Now we will come to this one. Okay. Go ahead.
So, okay, so when you do that, you react with.
Anyways, we have to form MgCl, right? So if you want to form MgCl, definitely you have to add chlorine to benzene ring. So for that, we will add Cl2
CO3.
FeCl. So it will come, chlorine will come here. Okay, chlorine will come here. Again, we can use magnesium or dry ether, right? Magnesium or dry ether. So what will happen? Magnesium will be inserted in between benzene and chlorine MgCl. Now, if you put D3O plus, that is fine. Yeah?
Okay.
Okay. Yeah. Okay. Now we will move to next one. Right, so can you try this? Let's say we have CH4, methane is readily available in the laboratory. So from this, we have to form this one. CH3, C double bond O, OH. So if you can observe this conversion, here the number of carbon is 1, here 2. So we have added one more extra carbon. So if the carbon difference is 1, we can either use KCN or HCN. Have you studied about KCN, HCN?
Sorry?
So if you use KCN, what will happen?
Potassium.
The Cl group will become CN group, yeah?
Okay.
Did we study that? If you want to convert Cl to Cn, we simply use KCN, right?
Okay.
Right. So it doesn't matter, even though you don't study, if you practice more and more conversions, automatically it will come to you, right? So we will start. So whenever you see this methane, you can prepare Grignard reagent, right? So Cl2, Cl2, sunlight, right? Sunlight. So we produce CH3Cl, CH3Cl. Now we can go with this sodium derivative also, but sodium derivative cannot be applied here because from this we cannot use any sodium derivative. Why? Because it can only react with two types, right? So if you have to have, we should have this C triple bond CH system, then only we can produce sodium. So sodium derivative cannot be applied here. Yeah, sodium derivative cannot be applied here. So we can either go for Grignard reagent or KCN or HCN, right? So we'll see how we can do this. So if you have KCN or sometimes HCN is also possible. So if you have KCN, what will happen? This Cl will become CN, right? So now we have added one more carbon to CH3, right? So CH3, CN. Now from the CH3CN, if you add H3O plus, it will directly become, CN will become yeah. So if you have CN, we have studied, right? So if you have CN group, what will happen? This H3O plus will be added as O2 minus N2H plus, right? So this H3O plus will release as, this is actually a theory. I don't know if I have taught you or not. Okay, you just forget this. We will move to the next method. Okay. Because for performing a conversion, there might be multiple ways. Okay? So one way is, you just remember, if you have CH3, CN, to a CN group, if you put H3O plus, it can be added as O2 minus and 2H plus, right? To this carbon, because this nitrogen will release and this double bond O will come here and this will be formed, right? So you don't, I think I haven't taught you this. You just forget this. We'll go with this Grignard reagent, right? Okay. So we have studied Grignard reagent. Now, if you put magnesium dry ether, it will become CH3MgCl. CH3MgCl. Now, if you want to add one hydrogen more, if you have to add one more hydrogen, you can go for this dry CO2. What will happen? We will have CO double bond O, right? MgCl plus CH. Yeah, CH. Is that clear? Okay. Right? So again, what you should do, if you put this H3O plus, what will happen? This will become H. So OH is here, and this double bond O is here, and CH3 is here. Is that clear? Is it confusing?
No, I'm just trying to fully understand it right now.
Okay. So after preparing this dry ether, we have to simply add, after preparing this Grignard reagent, you can use dry CO2, right? So if you use dry CO2, because the orientation of the molecule might be different. That's why you confuse here, right? Now, if you put this here, C double bond. Okay, so if I draw like this, you can easily understand. C double bond O, and here OMgX, and this CH3 will come and join here, right? CH3 will come and join here. Now, what is the difference here? Here CH3 is here, CH3 is here. This group is also here, this group is also here. But the only difference is here MgX has become H. For that, we simply add H3O plus. That's what we studied already.
Okay.
Yeah. So
Yeah.
this is how this conversion should be done. Okay.
Okay.
And we can do this in multiple ways also. As I told you, if you use this H3O plus to Cn after, I don't know if I taught you this KCN.
Sorry?
Teach you KCN. But anyways, you have understood how to perform this conversion using
Yeah.
dry CO2. Yeah.
Yeah.
Okay.
So
And we can
okay.
incorporate the previous reagents also, right? So we can find some alternative ways also. But now we will focus only on Grignard reagent, and then we will try to incorporate the previous reagent to the conversions that we have written here, right? So sometimes if you have prepared this alcohol, we can use PCC to convert it to ketone. And then from the ketone, we can do some other things, right? So we will try to implement everything we have studied in conversions. Okay.
Okay.
Now I will give you some questions. You can try them. And there will be a lot of conversion tutorials on YouTube also. You can watch them, right?
Okay.
And next class, we will focus on some conversions. I have a lot of conversions. If I
Yeah.
can give you the pictures also, right? So you can
Okay.
get them, but that might seem complicated, but that is nothing, right? So if you see a big conversion, it might.
Mm. Okay, inshallah.